Hi, I'm Pat Kelly. Okay, this was a four-part problem. In each part, they gave us this same y equals square root of x, y equals 0, x equals 3. That created this bounded region. And the four different parts of the problem were just spinning that region around a different axis of revolution and then asking us the volume. Finally, part D is what we'll look at in this video. What happens when we take that region and spin it around x equals 6. If you're just joining us, I did some work in an earlier part of the problem and took this equation, solve for x. I did that so that I'm seeing this top curve as a function of y. That might be important, okay? All right, so if I'm going to set up my integral here for the volume of this thing when I spin around x equals 6, I always want to make sure I start with the right formula. So in order to decide which formula to use, draw your representative rectangle first. So if I'm spinning around x equals 6, it's a vertical line, I'm going to draw a horizontal rectangle. With the disc or washer method that we've been learning, you always want to draw your rectangle perpendicular to your axis of revolution. Okay, that immediately tells me one thing. I'm going to integrate with respect to y, because the thickness of that rectangle is a y value. Second thing it's going to tell me is whether it's washers or discs. In order to decide, I'm going to take that rectangle and imagine spinning it around this axis of revolution and seeing if it's a disc or if there's a hole in the middle, which will mean it's a washer. Your drawings don't have to be perfect, but what I'm picturing is the left side of this rectangle spinning all the way around, and then the right side of this rectangle spinning all the way around. Not perfect as advertised, and the important thing there is just that it is a washer. There's a hole in the middle. So now that I know I'm going to integrate with respect to y, and it's the washer method, I can try to get my integral set up, which is always pi integral from c to d. The outer radius as a function of y squared, subtract the inner radius as a function of y squared. dy. Okay, that's the right formula. Now we want to make sure we put the right things in the right place so that we'll be able to evaluate that integral. As I get rolling here, trying to decide what to put in what place, you can see right off the bat I need limits of integration. The lower limit is going to be your lowest value of that variable that you're integrating with respect to. So back to my drawing, the lowest y value is 0. That'll be my lower limit of integration. D, the upper limit of integration, is going to be your highest value for that variable that you're integrating with respect to. So back to the drawing, the highest y value is that square root of 3. Okay. Now moving inside the integral, capital R, you should know, is the outer radius. But you have to do a little bit of thinking in this problem in terms of how to express that outer radius. I'm going to take a look at this washer, and the outer radius is going to be from the middle all the way to this outer edge. And I'm going to slide up to my drawing and try to see where that comes from. So up here in the drawing, that comes from this distance, the axis of revolution, all the way out to that left side of this rectangle. And I say to be careful because what we do know here is the left side of this rectangle that lies on this curve. That comes from this function, but this function gives us an x. And x is always what you're measuring from how far off the y-axis you are. So this is x. Trying to make sure you're being careful because I need this, and that function is going to give me something that I don't need. I don't need that segment. I need this segment. But it's going to help me get this length because what I do know is from here, this axis of revolution, all the way over is 6. I know that's 6 because that's x equals 6. So now I want this, where my hands are. And I know 6 here, and I know this little blue x. So I'm going to take 6 and subtract the blue x. That's a hard part to set up. See if you can visualize that. So I'm going to have for my outer radius, the big R, 6 subtract that blue, which is my function, and I need to express it as a function of y. So I'm going to grab the y squared. Back to the formula. That's all squared. Don't lose sight of that. Okay, and then continuing in the formula, minus, and then that little r, the inner radius. Come back over to my drawing with my washer. The inner radius is from the center of the washer to this inner rim. Let's see where that comes from in our drawing. This hand is at x equals 6. This hand came from our x equals 3 line. So the distance between those is going to be 6 minus 3. That was the space of my hands. Come back over here, that's my little r. Don't forget to square it though. It's in the formula. Okay, put some square braces here to include everything in my integrand. And that's the setup for this integral, which is probably the harder part of this problem. Make sure that makes sense to you. Okay, let's do just a little bit of cleanup then, some algebra, and then we'll get to some calculus. I still have my pi, integral 0 to square root of 3. The algebra cleanup, so I'm going to go ahead and FOIL this. If you'll let me do this, I'm going to do a little bit of arithmetic in my head as well. I'll FOIL this and get 36, but then I'm going to be subtracting 6 minus 3 is 3, squared is 9. So 36 take away 9, 27. Continuing with my FOIL, minus 12y squared plus y to the 4th. A little bit of algebra cleanup, and now we get to do some calculus, finally. This equals, we're just going to integrate. The pi is still there, 27y minus y cubed is going to bump up a power, and then divide by 3. So let's simplify with the 12 that's there. Plus y to the 5th over 5. And this is all still a definite integral from 0 to square root of 3. Okay, now we'll evaluate that expression at the upper and the lower limits of integration. My pi still. Putting in the square root of 3, 27 square root of 3 minus square root of 3 cubed. That'll give me one factor of 3 out of there. I'll multiply by the 4, and I'll still have a factor of square root of 3. Plus square root of 3 to the 5th power, 2 factors of 3 that'll come out of there, and one factor of square root of 3 still. Divide by 5. Those parentheses there. Okay, really arithmetic. Subtract what happens when you plug in that lower limit, but our lower limit was 0. They were being nice to us there, so that would have been 0, 0, 0. So there's really a subtract 0 there. Now I'll just clean up a little bit, which if I wanted to go to a calculator I could, but I'm feeling brave enough. 27 square roots of 3, take away 12 square roots of 3. That would be 15 square roots of 3, and I'll get a common denominator of 5. That puts me up to 75 square roots of 3 plus 9. Looks like 84 square roots of 3 over that common denominator of 5 that I got. And then just don't forget that factor of pi as well. And that I like as my final answer. Thanks, and I hope that helped.